Hello students, in this video we'll see an example of how to solve a constant coefficient ODE with both complex and real roots. Let's consider the ODE 4y triple prime plus 12y double prime plus 13y prime plus 10y equals 0, which we can write in our differential operator notation as 4d cubed plus 12d squared plus 13d plus 10 applied to y is equal to 0. Now we know the possible rational roots are plus or minus the factors of 10, 1, 2, 5, and 10, over the factors of 4, plus or minus 1, 2, and 4. So for example, we could have 1/4 as a possible rational root, 5/4 as a possible rational root, 5 as a possible rational root. So we have all these possible rational roots to test. Let's test, after some initial experimentation, we find that testing 2 or -2 will be helpful. So if we test -2, we'll put the -2 in the box. Then we'll have 4, 12, 13, 10, the coefficients of the polynomial we start with. We always bring the first number down, so bring 4 down. Multiply and then put in the next slot. -2 times 4 is -8. Then we add these numbers together. 12 and -8 is 4. -2 and 4 is -8. 13 and 8 is +5. And then we have a -2 and 5, which gives me a -10, and that gives me a 0, and that tells me that we have a root. It also gives me the factorization of our operator as d plus 2, and then 4d squared plus 4d plus 5 applied to y is equal to 0. We can find these roots by using the quadratic formula. Which will tell me that d equals -b, -4, plus or minus the square root of b squared, so that'll be a 16, minus 4ac, so I have a 4 times 4 times 5, so minus 4 times 4 times 5, all over 2 times a, so that'll be an 8. So we will have a -4 plus or minus the square root of 16, and then I have 5, so I'll have a 20 over here, and then a 4 over here, so that's -80, all over 8. 16 minus 8 is 64, so this is -4 plus or minus I, and then the square root of 64 is 8. So I'll have that over 8, which simplifies to -1/2 plus or minus I. So we'll have two complex roots. So now we're in a position to write down the solution of our problem. The solution of our problem will be y equals c1 e to the -2x, which comes from this factor over here. And then I'll have the two complex solutions. We'll have the complex solutions, which come from these terms over here. I'll have a c2 e to the -x over 2, that's the real part, cosine of x, which is the imaginary part, and then a c3 e to the -x over 2 sine of x. And these terms come from my quadratic expression and my complex roots. So this expression over here, this equation, is the general solution of our ODE. Thank you very much.